Hello, in this tutorial I am going to talk about how to use the C++ and Python languages in various basic numerical methods. In this video we will look at the Newton-Raphson method, which is very widely used in order to find the roots of equations. Let's start by looking at the Wikipedia page of this method. So we have a very nice animation here. In this method we have a function whose derivative we can calculate and is continuous. Then we have an initial guess of the root of the equation. The root is the value of x at the point when the function crosses the x-axis. We start with this guess, then we compute the y value of the function at this point. Then we are going to calculate the slope at this point, and we are going to follow this straight line until we reach the x-axis again. This is going to be the new value of the solution, which we call x2. Then we calculate the y value of the function at this point, and again measure the slope. Then we are going to follow this line until we cross the x-axis again, and we get the new guess. And so we repeat this procedure until we approach the solution, which would be this value over here. So this animation, here we have the author. So we have our method. How are we going to compute the new values of the roots at each iteration? First, we expand the function in a Taylor series. We have the more terms we add to this series, the more this expansion is going to approach the original function. In this case, we are only going to keep the first two terms. This is called a first order approximation around the point xi. Our first value is a horizontal function, and our second value is a straight line with a slope f prime. So then we are going to find the x value of this function at which the function crosses the x-axis. So for that purpose we make the function be equal to 0, and the x at this point is going to be called xi plus 1, which is a new value of x. So then we are going to solve for this variable, and that's how we get our formula for the Newton-Raphson method. Then we are going to repeat again another expansion, but this time is going to be around the new value of the solution. And then again we are going to make the function be equal to 0 for this new expansion and solve for the new value of x, xi plus 2, and we have in this way our iteration. So how are we going to calculate the slope of the function in a numerical way? We can use one of the most popular ways is called the central difference approximation. We start again with the Taylor series expansion for the function. Then in this x value we are going to expand this function both forwards and reverse in the backward direction. So we are going to calculate the function at a little bit to the right of our value and a little bit to the left. Then so in this x we will substitute this value, so we see that these two x's cancel each other and we end up with this expression. Then we are going to subtract the backward expansion from the forward expansion. This term is going to cancel with this one, and this term and this one is going to become twice. Finally, we solve for this slope. So we have the function evaluated a little bit to the right of our value and a little bit to the left, and we divide by twice the step in the horizontal direction. How do we know if the solution is the right one? We need to measure the error in our iteration. So for this purpose we can use the percentage relative error procedure. In this case we do not know what is the true value, so how do we determine the error if we do not know the true value? We have all we know is the solution approximation at each new iteration. So we can subtract the current value of this iteration minus the value in the previous iteration and divide by the value in the new iteration times 100%. These iterations are going to stop once this error is smaller than a certain percent tolerance, and that means that the value is converged, hopefully to the true value. So let's start our code. We're going to write. We're going to start with C++ code. So we're going to work at the same time with C+ and Python, so we can look at the differences. Let's start with the C++. First we will include the input-output stream, which is necessary in order to print into the console. We will use namespace standard. Then we write our main function. We want the result to come from a function called Newton-Raphson, to which we are going to supply a function, let's call it f1, and a guess of the initial value of the root inside of the iteration. So let's start writing our Newton-Raphson function. It's going to return a double. Is going to receive a function which we will call f. Is also going to receive an initial guess of the solution, also a step in the x direction, which is necessary in order to measure the slope, and also a tolerance for the error, and a maximum number of steps, because we don't want us to enter an infinite loop. We want, if we cannot find the answer, we want the program to stop. It's going to return the solution. So this function is not part of the standard library. That means we have to define with the type def instruction, we will define a function which is going to return a type double. We will call it function. It's going to receive a double, and that's enough. So in this way, it is possible to have a parameter, a function as a parameter of another function. This is very useful if we want to send a function to another function. So let's define our function f1. Is going to be double f1. Also the input will be double, will be x, and then it's going to return some function which we will write later, and that should be enough. So notice how here I only send 2 parameters, but here we have a lot. So we actually want some of these to have a default value, so we don't have to send them every time we call the function. We have only the 2 first parameters are the most crucial. The step in the horizontal direction to calculate the slope, we can make it a default of 1 times 10 to the minus 8. Let's give the same value to the tolerance, and the maximum number of steps, let's make them 1000. So in this way we can have both, we can send all of the parameters or only the first 2 as we prefer. So now here that should be enough for now. Let's see how this is going to look if we write a Python script. First we are going to import numpy as np, and we also want our solution to be very simple, Newton-Raphson. We will send a function inside a string and a guess of the solution. So we are going to define a function called Newton-Raphson. It's going to receive all of the same parameters. We have a function, we have an initial guess of the solution, we have the displacement in the step to compute the slope with a default value 1 times 10 to the minus 8. We have a tolerance also with a default value, and we have the maximum number of steps, and this is going to return the solution. Notice how we are sending a string. We are going to send a string which should be evaluated into the function. So for that purpose we can define a nested function inside the Newton-Raphson function. We can call it f, which is going to receive the x value and is going to return the y value. So with the eval instruction we can evaluate a string as if it was a Python code. So and this is going to return this value. So this should be the equivalent codes for all of these. Now we want the outputs of our program to consist of 3 columns. All of them should be aligned and with width, a specific width, so it is easy to read. So we are going to define a function that is going to output 3 columns. The first one will be the column of which iteration we are right now, what is the current value of the roots, and what is the percent relative error. So let's write this function over here. Voice out is going to receive 3 strings, s1, s2, and s3. It's going to output into the console the first string, but in this case, if we want the 3 columns to look nice with a specific width, we need to include a library called input-output manipulation. So in that case, we can use this function set width to 15 characters, and then we use the same for the second string and the third, and we end the line, and that's it. So then we can also output the initial values. The first iteration is going to be 0. The second iteration, the first root, is going to be the value of R0. However, this is a double type, so we need to convert this to string in order to print with our function. And the error at first, we are going to need to define 3 variables: the root, the slope, and the error, whose initial value will be 100. So then we are going to convert the error into a string. Okay, let's write this in the Python script. We are going to define another function with the same name, out. It's going to be nested inside our method. It's going to receive 3 strings, s1, s2, s3, and then there is a instruction called format, which can print 3 columns with the right alignment. So if we write this, format s1, so this is going to print the s1 variable with in a column of width 15 characters and with alignment to the right. If we change this like this, then the alignment is to the left. So then we do the same for the second value and the third. So then we can call this function to print the same instructions as over here: iteration, root, and percent relative error. In this case, we don't really need to convert to strings. This is done automatically by the print command. We haven't defined this error yet, so let's just send 100, which is the initial value of the error. So now the 2 scripts are, the code, C+ code and the Python script are equal at this point. Now we are going to start our loop. We will define an iterator starting with 1 until it reaches the number of steps and increases by 1. First, we are going to compute the slope. So let's have another look at our function. 1 step to the right, 1 step to the left. So we have one step to the right from the initial value minus one step to the left from the initial value, and then divided by twice the value of the step. And then we are going to calculate the new value of the root. So we have the previous value minus the function divided by the slope. So minus the function at this point divided by the slope. And then we will calculate the error, the current value minus the previous value over the current value. So it's going to be current value minus previous divided by current, and this should be the absolute value. And then we are going to output the result. This is going to be the current iteration converted into a string, and this should be the current value of the roots. So, and then we are going to stop this this loop if the error becomes smaller than the tolerance. And that should be enough. So in our Python script we can actually do almost the same thing. It won't change a lot. Here we are going to write for the iterator in a range of from 1 to until the number of steps. This function stays the same, this one as well, this one as well. The outputs we don't need to convert into string anything. However, it will look nicer if we round this number to 6 decimal places. Okay, and we need to delete every semicolon and add a colon at the end of each instruction. So I think that should be enough. Then we can define a function. I was looking at the function that looks nice. It's exponential to the minus x times x plus 10, and then we write the same function in our C+ code. Exponential to the minus x times x plus 10. Wait, this one should be plus. So in the C+ codes, if we want to use the exponential function, we need to include another library called algorithm. And I think now it's ready to run. Let's see what we get from our C+ code. Wait, it looks like yes, we also need to update our value of the root every iteration. Okay, so now we run our code and we get the solution to be minus 1.745, which was obtained at the 16th iteration, at which point the error became smaller than the tolerance. Then we do the same for the Python script. First we right? And so then we get the same result. Let's now make sure that this is the right answer. We can make a plot of the function with the GNU plot. We're going to plot from -2 until -1.5 the function exponential of minus x times x plus 10. Then we can put the grid, and we see that in this at these points -1.745 the function crosses the x-axis. So thank you very much for watching. I hope you enjoyed and have a very nice day.